Hello everyone. Today we'll be talking about sections 1.6, transformation of functions. As you will see, I'm going to go through the objectives with you as we will selectively go through each graph as you will see the transformations. So let's start out by the objectives. Objective 1 will be to recognize graphs of the common functions. Objective 2 will be use vertical shifts to graph functions. Objective 3 will be use horizontal graphs to graph functions. Objective 4, use reflections to graph functions. Objective 5 will be using vertical stretching and shrinking to graph functions. Objective 7 will be to use horizontal stretching and shrinking to graph functions, as well as the last objective will be seeing how these graphs of functions involve a sequence of transformations. So what we'll look at first is objective 2, which will be looking at vertical shifts to the graph of functions. As you can see, I will start off graphing each function by a basis of which we will call the parent function. In this case, the basic function is the absolute value. And you will note to the side of it, you will notice the transformation. In this case, the transformation is a downward shift. But let's go back to look at how the absolute value graph actually looks. You will notice that as you identify the absolute value, it looks like a V. So when you move over to the transformation, we're still dealing with the parent function, which has an absolute value, but I want you to take note of how the graph went downward, -3. So let's take a second to look at how this graph looks as we animate and shift the absolute value graph vertically upward as well as downward. Okay, as we come back, you will see that we have the parent function of the absolute value, which is also known as our common function. I will note throughout the session of the actual common functions that we'll be looking at, but as you can see, we will start with the absolute value function and how a vertical shift occurs. So looking at our absolute value function, I'm going to show you how you can animate the actual transformation itself. So notice as I click on the actual icon, you will see how the absolute value graph is going at a negative, which is downward, and positive, upward. Also, I want you to take note of the actual effect of the constant, and you will also see after it crosses the origin of how we have a downward shift. So this is one of the transformations that we will discuss throughout this section, which is a vertical shift. Another transformation that we will talk to or actually look at will be a horizontal shift. So at this time, let me show you how a horizontal shift may look. So now let's take a look at the horizontal shift. Again, we're still focusing on one graph, which is the common function graph of the absolute. Again, the origin starts at 0, 0, but now let's take a look at the transformation that actually takes on horizontal. So if you look at the horizontal shift, you will notice that the absolute value with the function of g of x equals the absolute value of x minus 2, it's a transformation to the right. Now, previously we talked about the transformation with a vertical shift upward or downward, and in this case, we're talking about a transformation either to the left or to the right. But you will note that the minus sign seems a little peculiar since we are usually known to see that a positive will indicate that your graph would be on the positive side. But in this case, when you're doing a horizontal transformation, you will note that your constant will go opposite of what your actual sign is. So in this case, x minus 2, it will actually have a transformation where you will see the constant at 2. So again, let me show you how we can animate this graph using an actual animation of the constant for the horizontal shift. as we look back at our graph, we will see how a transformation horizontal shift takes place. Now, let's just recap looking at how the vertical shift occurred. But also note, we will continue to look at that as look at the continual shift of a upward and a downward. But I'm going to also show you how simultaneously it may look horizontally. So now let's stop and take a look at solely your horizontal. And notice how your horizontal shift is x plus 2, and then note where it's x minus 2. You will look at the function and how it shifts from left to right based off of its transformation. But also note that the constant sign changes, and in this case it's minus, even though it's on the positive side. Now, horizontal shifts and vertical shifts play a key role in transforming functions. So I'm going to show you back of how these work simultaneously. So, an overview. I want you to take a look at vertical shift. Shifts outside the function are vertical shifts with the sign. So again, if it's up, it's a positive constant, which you will see based off of your function. If it's negative, it's down. If it is horizontal shift, note, shifts inside the function are horizontal shifts with the sign. In this case, if it shifts to the left, you have a positive sign that correlates to your function given, as you see here, f of x equals the absolute value of x plus 2. If it's minus, you will also take note that your sign that is inside the function, in this case, would be minus. So in this case, you would see vertical shift and horizontal shifts that take, showing you simultaneously as they both look once again. Now, as we go through the section, we will move on now to another kind of transformation, which will be known as reflection about the axis. We're going to talk about two reflections, which in this case would be a reflection about the x-axis. Another reflection that we will talk about is a reflection about the y-axis. So, as I mentioned earlier, we will be always starting or deriving our graphs from our common function or our parent function, which in this case is f of x equals x cubed. As you will note, when we reflect f about the x-axis, you must replace each y-coordinate with its opposite sign. Now, let's visually take a look at the actual point that lies on the f of x equals x cubed common function graph. You will note that 1, 1 is on your parent graph. However, if you were to reflect f about the x-axis, remember that you replace each y-coordinate with its opposite sign. So now 1, 1, which is on f of x equals x cubed, has now or will be shifted to the point that you will see on the red graph, which is our transformation reflection about the x-axis, which is 1, -1. You will also note that in this case, you will have another point, which is -1, 1. And you can note here again that the point is 1, -1, and you will see that the points are actually reflecting each other from the x-axis. Another point that we'll take a look at is the graph of f of -x is obtained by reflecting the graph of f of x about the y-axis. Now, in this case, we're going to take a look at the common graph known as a square root. So we'll look at the black graph that denotes f of x equals the square root of x. Now, that is my common function. But in this case, as we take a look at the transformation, g of x equals -x. you will see that reflect x about the y-axis, you must replace each x coordinate with its opposite sign. And in the same case, you will note x here on the point of your parent function graph, you can see 1, 1, again as a point on the parent graph. But note that for the reflection, your point for x can be denoted as -1, which is a reflection about the y-axis. So key notes to take on is that when you reflect about the x-axis, you must replace each y-coordinate with its opposite sign. As far as the reflection about the y-axis, you must replace each x-coordinate with its opposite sign. So now, as we've taken a look at reflections, vertical shift, and horizontal, we will now move on to talking about vertical, stretching, and shrinking reflections. As you will be able to see, we will start with our common function as known as f of x equals x cubed. Note that in this case, we're going to do a vertical shrink. Vertically shrinking the graph of x, you must multiply each y-coordinate by 1/2. And you will note that the black function is known as our common graph, as our red is noted as our transformation. So when I have my function, which is my parent function, x cubed, I'm going to start out with a point. Say, for example, my x would be 1, 1. Or I could take a note at looking at the y on the parent graph. Now, my y is at 6, as you can see. But if I was to multiply each y-coordinate by 1/2, you would note that 6 now for my y-coordinate will come down to 3. As you would see that 3 correlates to the point on the parent function. If I was to have 4, as you would see 4 is a point on, a y-coordinate of 4 on the x cube, you would also see that y will correlate to 2. So what you need to take note as, anytime you are doing a vertical shrink, the graph of f, you multiply each coordinate, in this case, the y-coordinate, by 1/2. Now, if we wanted to do a vertical stretch, you're taking the same case, but you're multiplying the vertical graph, the parent function as well, by 2. But there are certain rules that you must take note of when you are determining if it's going to be a vertical shrink or stretch, using or being particular with the actual constant function that you will use. So you may be asking, what made me decide to use 1/2 or 2? Well, there are restrictions in this case. Vertical stretching the graph of f of x if c is greater than 1. In this case, the blue graph, the constant, is c equals 3. So you will note that you have a vertical stretch, but it is a vertical stretch if your constant is greater than 1. In that case, it is only a stretch if you choose or pick your constant to be greater than 1. A vertical shrink of the graph of f of x, you will see the restrictions between 0 and 1. So note, the red graph, which you will see, 1/3 is a constant which has restrictions between 0 and 1. And that in itself will give you a graph of a shrink. In this case of the red graph, the constant is, like I mentioned, c equals 1/3. Therefore, you are having a vertical shrink. And now you may think and look at the graphs that we have here are a little bit different than the previous ones, but this graph is a common graph that you have possibly seen, which is known as the quadratic function graph, where you will see that f of x equals x squared is your parent function. And I have derived 2 transformations, which in this case, recap, the blue is the vertical stretching, as well as the red is the vertical shrink. Now we're going to take a look at the last transformation, which is a horizontal shrinking and stretching of a graph. Note, we'll take a look at our f of x, which is f of x equals the absolute value of x, which will be our parent graph in this case. Noting that a horizontal stretch, the graph of y equals f of x, we will divide each y coordinate by 1/3. Previously, we talked about vertical shrinking and stretching of graphs, where you were multiplying the constant opposed to dividing the constant in this case. As you will see, the parent graph, you could take a look at any point on the actual common function or the parent graph and divide each coordinate by 1/3, or rather your x coordinate by 1/3, and you will see that in this case it would give you an x coordinate which is 1/3 of the actual parent function. For instance, 6, 6 is a point that is on my parent function. But if I was to take that point and divide it by 1/3, you would note that now I would have an x coordinate of 2, which you will see my x coordinate is 2, and I would also have a value of 2 for my x coordinate, as well as 2, 2, which will be correlating to your x as well as your y. Now, for a horizontal shrink, you're going to do the same thing, but you have to take note of your restrictions that take place on your actual graph. Now, previously, we talked about restrictions for the vertical shrink and stretch of your graph. Now, in your constant case, you would have to see if your actual constant was greater than 0 or less than 1. In this case, your C constant is 1/3, which is actually less than 1, but greater than 0. Therefore, you would have a horizontal stretch. As a horizontal shrink, your C would have to be greater than 2. And you would note that, or excuse me, greater than 1. And in this case, my constant is actually greater than 1, as you would see that g of x equals 3 times x, the absolute value of 3 times x, which 3 is obviously greater than 1. So, recap, when you have a horizontal stretch, you have restrictions between 0, where 0 is less than c, and c is less than 1. As well as a horizontal shrink, you have to take note that your constant must be greater than 1. Now, lastly, we will put all of our transformations together and observe how it may possibly look when you are using a multiple transformations. Now, I will start off with, in this case, the parent function, which is x squared. Now, I'm trying to determine how I would get to -3 times x minus 2 raised to the power of 2. So in this case, you're going to see that there are going to be various kinds of transformations that occur. So originally, we have a parent function, which is x squared. Now, we're going to shift the graph of f of x to the right 2 units to arrive at the graph of f of x minus 2. So you will note that we started with x squared, which is our black graph, which is our parent function that we start with, or common function graph. Now you will look at the x minus 2, which was a horizontal shift to the right 2 units. Now let's take a look at what will we be doing in the next case to arrive at the next function, which would be h of x, which equals 3 times x minus 2 squared. Now note, you're doing a vertical stretch, the transformation that we just talked about on the previous page. So note that the vertical stretch of the graph is by a factor of 3 to arrive at the graph of 3 times f of x minus 2. Now lastly, we're going to go back to the reflections of the x-axis, which we've talked about previously in the lesson. Now note that you reflect the graph of 3 times f of x minus 2 about the x-axis to arrive at the graph of -3 times f of x minus 2. So you may ask yourself, well, what transformations did you use? Well, we went over an overview of all the transformations that you've actually went through the lesson, starting with your parent function known as x squared, which from there we did a horizontal shift to the right. Now, we took that into place and we took on a vertical stretch, which you will see the green graph. And lastly, we would take a look at the reflection of the x-axis to the graph. So you would notice that now the actual graph has flipped, considering the fact that you have multiplied the actual function itself by a negative. Now, as our final summary of the transformation lesson, you will be able to come to a table that will describe all of your transformations that will take place as you look at vertical, horizontal, reflection about the x-axis, reflection about the y-axis, vertical stretch, vertical shrink, horizontal stretch, and lastly, horizontal shrink. Again, take note that when you are doing vertical stretch and shrink, as well as horizontal stretch and shrink, there are restrictions that you must abide by when you're dealing with your constants. Now, key factors going back to vertical shift is that you are moving upward or downward. Horizontal shifts is meaning that you are placing your constant inside of your function and you're moving left or right. Reflection about the x-axis is that you're multiplying your function by negative f of x. And lastly, reflection about the y-axis, your function becomes f of negative x, which reflects the graph of f about the y-axis. As we concluded the section of 1.6 of transformations, I ask you to make sure that you go back and refer at any time you have difficulties as you look at the summary of the transformations placed on the last slide for this section. And also I ask you to seek help from your instructor in case you have any more further questions. Again, this concludes the section of 1.6 transformation of functions.